So I'll talk. Okay. Today I'll talk about joint work with Damek Davis and Liwei Jiang. Liwei is a student of Damek. They're both in Cornell. And it's actually about a fairly classical, well, not a fairly, like a classical topic in stochastic optimization dealing with asymptotic normality. But we will see the answer, like some of the questions that are being stated are very classical, but the answer is sort of not so classical as we'll see. Oh, and please feel free to stop me at any time because, even the notation or something like this is not clear. It'd be great if you stop me and I can answer some questions. I have my iPad with me, so I can even jump on an iPad. Okay, so the basics. I want to start with the motivation slide, and then I'll give a sort of outline slide about what the talk is going to be about. So the motivation comes from just very basic problem stochastic optimization. So the basic problem is you would like to find a solution, which I'll always denote by X star here, to a minimization problem where minimizing an expectation of a function f. You have the decision variable x, your minimizations over the decision variable x, and the expectations taken with respect to this auxiliary data point z that follows some probability distribution p. And for now, in this motivation slide, I'll assume that these functions are smooth in X. Okay, and the main assumption is that the only access that we have to the probability distribution P is by sampling. So we get to see a sample from P, get to see the corresponding sampled function F, with X, being dot comma Z, but for that sample Z. So that's the setup. Okay, and the most basic algorithm for solving these sorts of problems is the stochastic gradient method, that everyone knows and loves, which simply proceeds as follows. In every iteration, you sample zk from the probability distribution P, and then you walk in the direction of the gradient of the current sampled function taken at the current base point xk. So you go from xk in the direction of minus the gradient by a certain amount alpha k. It's important how much you go, but let me not worry about that for a moment. And so that's the whole process. Okay. And there by now there's so much understood about stochastic gradient. It's a really very, very classical process, and we understand more or less everything there is to understand about it. And so from 92 there's a fundamental result that tells us about the statistics of these iterates xk. And so that's what really this talk is about, or at least most of it. So you can think about, let me sort of hide this for a second. You can think about xk, right? The xk's are a random process, and they're supposed to be approximating the solution x star. So for any fixed k, xk is an estimator, okay, statistical estimator of the optimal solution. And so very standard question you ask when you have estimators is they're asymptotics. So they're asymptotic distribution. So if you rescale by, roughly speaking, by the variance, and then you want to see, what do the deviations look like? Do they converge to a random variable, for example, a normal? Okay, and so this is what was shown by Polyak and Juditsky in 92. And so this result says the following. So if you take it's important to take the following step sizes. So the step size should grow like k to the power minus beta, where beta is between one half and 1. Okay, so that turns out to be important. And let's assume that the Hessian is positive definite at the solution, so strong second order sufficient condition for optimality. And let's just suppose that we, if you have global kind of convexity properties, then you'll be sure that these iterates xk will converge almost surely. Then under some second moment assumptions, the following is true. So if you look at the average iterate, not the iterates themselves, and this is important. So if you look at the average iterate, okay, so you average all the iterates, okay, you look at the running average, then, and I'll call them x bar k. So x bar k is the average of the iterates up to iteration k. And then you look at the deviation between x bar k and x star and rescale by the square root of the iteration counter. Then that converges in distribution to a normal. Okay, so we have asymptotics, very strong asymptotics for these deviations. So I'll explain what the variance is in a second. But already this tells you, gives you some information. It tells us that in fact even if you would normally expect like the rates of convergence to depend on the step size and like the beta, but in fact, if you average, they don't. So you have a certain acceleration that appears if you look at the average iterates, where the asymptotic rate of convergence is like 1 over root k. Okay, now what is the variance? So the asymptotic variance has a very simple form. It's composed of 3 terms, and it's actually important for the talk to understand what they mean. So the asymptotic variance has basically 3 terms. The left and the right are the same. So the middle is the effect of the noise. Okay, so the only place where the noise appears in this asymptotic covariance matrix is in the middle. So what is it? It's just, so you look at the gradient of f at x star, and you think about that as a random variable where the randomness induced by the randomness in z, and it has a covariance, right? So this is just the expectation of this vector times its transpose. So the outer product with the taken with expectation with respect to the z. Okay, so that's the effect of the noise. And then what this is a measure of sensitivity. So in variational analysis, we'll recognize this as measures of metric regularity and so on and so forth. This is telling us how sensitive is the solution of f to tilt perturbations. So if you wiggle big F a little bit, this has nothing to do with the noise, right? So F is some function. You can have lots of different probability distributions giving you the same function. So this is just the Hessian of F inverse. So it's giving us some sensitivity information about how stable the solutions are to perturbation of big F. Okay, that's the background. Okay, and then there are many other reasons why this is important in order to establish, confidence regions, so on and so forth. So there are many sort of fundamental reasons why such asymptotic normality results are very important. Okay, and in fact, the asymptotic covariance sigma is best possible among any estimator. So this tells us that the stochastic gradient method, as simple as it is, asymptotically is best possible, and there are formal ways to state this. I'll come back to one of them later on in more in greater generality called local asymptotic minimax. So I'll come back to that. So in a sense, this gives us a very precise asymptotic information about how good is stochastic gradient. And in a sense, it's the best possible asymptotically. Okay. Good. So that's the background. So the question now I want to ask is what happens when we have constraints or any kind of non-smoothness whatsoever? So if we have constraints, so if it's not just minimizing such an expectation, but rather minimizing such an expectation over a constraint set, or if you have a regularizer, a non-smooth regularizer, everything I'm saying will be for constraints, but you can imagine that everything extends over to regularized problems as well. So what happens? Can we talk about the asymptotic normality of the stochastic gradient method at all? Okay, and so if we have constraints, all you have to do really to modify the stochastic gradient method is to take a gradient step, but then apply a projection. So if we have minimizing over x in a constraint set x, you just do exactly the same algorithm, except after you take a gradient step, you apply a projection into the set. So that's what I mean by stochastic projected gradient method. So can we have any kind of asymptotics like that? And so the punchline of the seminar today of this talk is that the answer is yes, with some caveats, but the caveats are almost unavoidable. Okay, so at this point, I want to actually, so this is actually surprising, right? So if you sort of think about it, if you start projecting onto non-smooth sets, even the polyhedron, this process with the projection becomes non-smooth. It's not a smooth update anymore. And yet you will be able to show some asymptotic normality. And another interesting thing is that not all algorithms that may be natural are asymptotically normal with the right covariance. So it turns out that in fact, the motivation for this work was an algorithm that was not optimal, did not have the right covariance. So there was a paper of Ducci and Ruan in 2018, which showed that a very natural algorithm called dual averaging, stochastic dual averaging, it turns out that it actually gets the wrong covariance as soon as you have any curvature in constraints. Okay, it gets the right covariance, right? It does have asymptotic normality guarantees, but only for polyhedral constraints. Okay, so I want to illustrate this question and the answer just with an example, numerical example, because I think it will become clear where the nuance appears. Okay, so let's consider the following stochastic optimization problem. Okay, it's purely geometric, so everything, all the question and the answer are all going to be in pictures. Okay, so hopefully I'll convince you about what is happening. So what is this? So I'm going to just let's forget about the formulation for a second. So I have two balls that intersect, and they intersect in a pillow. That's my constraint. I have one ball, another ball. Right, so this is one ball around E1, another ball around minus E2, minus E1, and I intersect them. I get a pillow. Okay, so the pillow has a sharp ridge. Okay, so nonlinear optimization, we call this the active manifold, and we will be these constructions will become important as we go on. Okay, so this is a non-smooth set because it has this ridge. It's smooth everywhere except for this ridge. Okay, and what am I doing? What's the optimization problem? I'm basically just going to maximize up, so in the vertical direction. But I'm going to write the vertical direction as an expectation of a Gaussian, of a linear function with a induced by Gaussian. So it's the dot product of a Gaussian that's pointing, well, if I'm maximizing, it's pointing up. If it's minimizing, it's pointing down. Okay, so that's it. That's the whole algorithm. And so the way that I access this linear function is I sample. So I sample z from a normal with identity covariance and minus E3 as its mean, and then I take the dot product and so on and so forth. So I get these perturbed gradients that roughly all point vertically. Okay, and so what happens now if I apply the projected stochastic gradient method? So again, the projected stochastic gradient method just samples z, walks in direction of that z, in fact, or minus that z, because that's the gradient of the objective, and then projects back onto the pillow. Okay, so here's the sort of picture that appears, and this is what I'm going to explain. First of all, okay, this is the initial point. The iterates get very, very close to the active manifold. So this is the zoomed in picture to the pillow, to this bit. Okay, so the iterates get very, very close to the manifold. Okay, they get much closer to the manifold. They get faster, they get closer to the manifold much faster, and then they get close to the optimal solution. Then once they get to the manifold, they start jumping across it at very small step size and start kind of going, on a macro scale, it's the iterates start going tangent to the manifold. On a micro scale, they're actually going normal because it's quite slow, and eventually approach the solution. The points never hit this manifold of activity. They're always off it. Okay, but now let's see what we're interested in. So we're interested in looking at these deviations. So you look at the average iterate, you subtract of the optimal solution, and you rescale by root k. So if you look at that, what you see is the following. This is the covariance. This is the empirical covariance of these things, right? So if we're looking at essentially as k goes to infinity, I want to think about what at least is the covariance of this. Forget about the distribution, but what is going to be the asymptotic covariance? And you see it's supported along a line. This line is just the tangent line to the circle. And this picture, you can already see in this picture, it's just, you see that the normal directions are going to zero much faster than the tangent directions. It's because these points are approaching this manifold of activity faster than they're approaching the point. So the normal direction are actually decaying at a faster rate than root k. And that's why you only see the support appearing tangent to the circle, because the orthogonal direction tends to zero faster than 1 of root k. Okay. And now so that sort of tells us about something about the covariance. And now if you want to actually think about the distribution, we can think about what do the iterates look like within this tangent space, within this line. So I just take all the iterates, I project I project them onto the tangent line. I look at the displacement, look at root k, and draw a little histogram by rerunning the experiment many times. And we see clearly a Gaussian behavior. So that's what I mean by yes. So that's the answer. Okay, so this is what I'm going to do, is I'm going to explain all these pictures and why they occur in general. Well, with some caveats, but essentially in general. Okay, so this is the outline for the talk. So I'll begin with some notation. And then, okay, it's a very concise outline. So I'll begin with some notation. I'll begin with a kind of lower bound that says what we expect. So this part, so everything here in 2 is well known, and this is just essentially a review to tell us why, what kind of asymptotic covariance we expect, what kind of asymptotic distribution we expect, and so on and so forth. And then and then there'll be one new part here that has to do with there are lower bounds for optimality. Okay, so there'll be one new thing here, and then finally the upper bound is kind of the punchline. So the upper bound tells us that yes, okay, that's the answer. Yes, okay, with these you get the right covariance, the best possible covariance for the projected stochastic gradient method under reasonable assumptions. So that's it. And asymptotic normality. And then, depending on how much time I have left, I will show you that the techniques that we developed to answer these sorts of questions are not confined to this question. In fact, they're much more general. They have to do with certain new regularity condition in non-smooth analysis, okay, in variational analysis. And they're used in other contexts. And if I have time, I'll talk about escaping saddle points and all sorts of stuff at the very end. Okay, so it turns out that the fact that we're dealing with optimization is not crucial at all. Really, we might as well be thinking about solving equations. The equation being that the 0 is equal to the expectation of the gradient, and the stochastic gradient method is just a kind of forward procedure in that process. Okay, so in fact, that's the most natural setting to be looking at, and so we're going to think about. We're going to go from optimization to a more general context of solving equations, because it turns out that's all that matters, and sort of that's kind of the right setting to be thinking about these questions. Okay, so we're going to be thinking about the setting of stochastic variational inequalities. So just sort of setting the stage. We're going to be thinking about finding a solution x star to an equation now. It's not an optimization problem, it's an equation. So what's an equation? Which equation we're talking about? So it has two components, okay? The smooth bit and the non-smooth bit, okay? So the smooth bit is going to be an expectation of some map A, x, z. So for us, before this was just the sample gradient. Plus the normal cone, and the normal cone, that's the non-smooth bit, that's the blue. So that's the general, the basic normal cone of outward normals to the set x. So if you're familiar with that construction, then great. If not, just think about x being convex. That's fine also. Okay, so I just drew a picture, so it's clear. So the set of outward normals. Okay, and so we're interested now in stochastic algorithms for this problem, right? So clearly, constrained optimization is an example where x is the constraint set and A is the gradient. And I'll assume that these functions A are actually Lipschitz in the first coordinate x, which amounts again for optimization, just Lipschitz continuity of the gradients. But x can be a very complicated set. Okay, and then again, like I said, the first main example is just stochastic optimization, where AX is just a gradient. But there are, of course, many examples of stochastic variational inequalities, like, for example, finding Nash equilibria, where this A would be kind of stacked gradient of different functions, which itself is not a gradient at all. Okay, good. And so the projected stochastic gradient method for solving equations now takes exactly kind of the very similar form, or sometimes called, it's not really called stochastic gradient method. There should really be called stochastic backward algorithm, but let's just call it stochastic gradient. And so what you do is you just walk in the direction of A, like the gradient. All right, so you sample zk from P, you go in the direction of A, xk, zk, and then you project back into the constraint set. So in context of optimization, this is just the projected stochastic gradient method. Okay, if something's not clear, please interrupt me at any time. Okay, and so what we'll be looking at, P sub x is the projection, so nearest point projection. So what we'll be talking about is this process, this algorithm. Okay. So, like I said on the very first slide, in order to even understand what happens in the limit for these sorts of iterates after scaling and averaging, we need to understand what do we expect to happen, right? What's the best possible that we can hope to happen? Well, it's known very classically now from the 80s, late 80s and early 90s, I suppose. The asymptotics of any stochastic process for this problem really depends on how stable the solution is to perturbation. Okay? So it depends on all the things we like in variational analysis, solution maps, metric regularity, and so on and so forth. And so let me sort of explain that if you haven't seen that before, because it will be important as we go on. So really, if we think about the right-hand side as a set valid map, okay, we're looking at solving the equation 0 lies in g of x. So g of x is this particular set value map. And what really matters for asymptotics is how stable are the solutions of this system, 0 inside g of x, if I wiggle the left-hand side. So if I wiggle v. Okay, so quantitative measures of the stability will appear in the asymptotic covariance if we're so lucky to have asymptotic normality. Okay, so in particular, in order to truly have normality, like really have asymptotic normality and not other asymptotic distributions, it's basically essential that this operation of going from v to g of x, that's a smooth map, smooth single valid map. So that's the assumption I'm going to make. So without this, you can get asymptotics for various algorithms like sample average approximation, and this has been done in the 80s. But you do not have normality. You have other distributions that appear. Okay, so the assumption is that for every v, okay, excuse me, so this is kind of the graph of g, and so the assumptions, we have a localization. So if we sort of zoom into the graph of g and we flip the x-axis and the y-axis, that looks like a graph of a smooth map. So in other words, so again, in language of variational analysis, this is just saying that the map G admits where the G inverse admits a smooth single valid localization. Okay, so the solution should be invertible for small v near x, with solutions near x. And so that solution, that operation that goes from perturbations of the left-hand side to solutions, I'll denote that by sigma. So sigma is the solution map, localization of the solution map. And again, in the context of optimization, these are tilt perturbations. So this is just saying if you add to your objective function a linear function, and you look at how does the solution vary with respect to the slope, to the linear bit of the function, to the linear function, you want that dependence to be smooth. Okay, so what is known? So the best really we can probably hope for is what we're looking at sort of dynamics. So maybe it's sophisticated dynamics, right? So this algorithm, but okay, it cannot be better presumably asymptotically than the simplest thing you can do, which is the sample average approximation. So let me review sample average approximation quickly, because it will tell us what we expect to happen and what are the natural assumptions under which good things happen. Okay, so an alternative to these kinds of online algorithms like the projected stochastic gradient method is just a batch algorithm, which simply in the beginning samples draws k samples, z1 through zk, according to the probability distribution p, and then it forms the average, empirical averages of a's. So this is like you're approximating the expectation. Okay, and you're solving this equation. So xk is now going to be a solution to this equation. So it's been known for a while that there is asymptotic normality for this problem, and the normality looks, and the result looks like this under mild conditions. If you look at xk, so it's the solution to this empirical version of the problem. You look at xk minus x star, and you rescale by root k. That converges in distribution to a normal, which is what we want. So let's look at the covariance. This is the important bit. So the covariance looks just like in a smooth case, except, okay, so you have the covariance of ax star z. That's just if we had no constraints, it would be the same thing as before. And the only thing that happened is now we have this new measure of sensitivity, which is the Jacobian of the solution map appearing. So before, on the very first slide, we had exactly the same formula for just a smooth optimization, except the Jacobian of sigma 0 was the Hessian inverse. Now we have a more general setting where the Jacobian of sigma 0 is just the Jacobian of the solution map. Okay. Okay, and in fact, there are many, maybe I should have mentioned this. So the fact, the smooth invertibility, so typically in variation analysis, we don't really talk about smooth invertibility, we think about Lipschitz inverses. But smooth invertibility is very natural, and it appears very often. If you haven't thought about it, it might sound strange. I mean, everything is non-smooth, but having smooth inverses is very typical. I'll come back to that point shortly. So it comes from, yeah, I'll come back to that point shortly. I'll convince you that smooth invertibility is somehow a very natural, very reasonable thing. And unavoidable if you want normality, true normality of solutions, of estimates. Okay, so in fact, so we know how this very basic process of sample average approximation works. It has it achieves asymptotic normality. It has a covariance. So a very reasonable question to ask is this covariance best possible among any estimation procedure? So morally, yes, it should be, right? What can you do better than asymptotically than sample average approximation? Yeah, and in fact, this is true. So there's a formal way to state this. Don't worry so much about the details, but there is a notion of local minimax optimality that's due to Ajek and Lacan. And so in a very precise sense, this asymptotic covariance is best possible for any estimator. Okay, so let me skip the details about what that means. So, okay, but the main point is the following. Sample average approximation, it will be asymptotic normal under all these assumptions with the covariance that we understand really well, and it's best possible. It cannot be improved. So the best we can hope for, so we know what we hope for. We hope for that the projected stochastic algorithm achieves exactly the same guarantees as the sample average approximation, and therefore is best possible, asymptotic. Okay, and so I will show you that indeed this is the case. Okay, and so what I want to do is I want to just do an example. Come back to the running example we had. So just to explain what is this Jacobian of sigma and so on and so forth, if you haven't seen it before. Okay, so let's look at the problem we had in the very beginning, which was minimizing our function f of x, which was this expectation in particular of the linear function. So this is the picture from the very beginning. You have two balls. You're minimizing. You're trying to go up for the pillow, right? So the intersection is a pillow. You're trying to maximize up, and you're going to get this little star. Okay, so let's interpret the Jacobian of sigma and all these things for that, just so that we're all on the same page. Okay, so this is an example of nonlinear, a standard problem of nonlinear programming. So you're minimizing some smooth function f subject to a bunch of smooth inequalities. The two smooth inequalities are just the quadratics. The first quadratic is defining the first ball. The second quadratic is defining the second ball. Okay, so as a standard, let's define the active index set. So this is the set of indices so that are active at the optimal solution. So at the optimal solution, gi x star is supposed to be 0, and I collect all the indices. That's the active index set. And the active manifold, which is in the picture, the circle, can be just understood as what happens if you take all of these active constraints and then you set them to be equal to 0. So instead of inequalities, you set them all, you take all the binding constraints and set them all to be equalities. And that just becomes this active manifold this is called M is called the active manifold, and here it's the circle. Okay, so the standard assumptions they usually puts is well, not usually, but we will. So these are the strongest assumptions you can put basically. So that the active gradients are linearly independent. The Lagrange multipliers are strictly positive, and the Hessian of the Lagrangian function is positive definite on the tangent space. So strong second order condition for optimality. Then this problem will be smoothly invertible. So the solution map will have a smooth localization, and the Jacobian of sigma is given in the usual way in terms of Hessians of Lagrangians and so on and so forth. Okay, so really, when we're talking about nonlinear programming, the assumptions we're making is linear independence of the gradient. Strict complementarity. Strict complementarity is crucial in order to have smooth invertibility of the solution map, and positive definiteness of the Hessian of the Lagrangian on the tangent space. So strong second order conditions for optimality. Okay, and then all our assumptions hold, and all conclusions hold as well. I didn't tell you what the conclusions are formally yet, but they'll hold in particular for nonlinear programming under these standard assumptions. Okay, good. Okay, so now So I need to explain now. So, okay, so now we're going to talk about the projected stochastic gradient method. Why is it asymptotic normal? Why does it achieve the right covariance? So in order to understand why this is not clear that this is true, or this is not clear why it should be true, it's useful to understand where does the asymptotic normality come for just sample average approximation. So for sample average approximation, the situation is actually very intuitive. So if you look, again, the sample average approximation is this setting. It's where you sample up front K. So you form K samples, you draw K IID samples, you form the empirical average, and you add and you solve this equation. Okay, so it's straightforward to see that if you just rewrite that equation, really what is happening is that you can recognize those solutions, those xk, so to empirical, the solutions of these perturbed equations, they themselves are images on the solution map of a small vector vk. There's a perturbation occurring. This vk comes from the error in approximation. You're approximating the expectation by the sample average. So there's a little bit of an error, but then, okay, if you mess with the error, then this is what happens. So you can write down xk as the solution maps, as the solution map applied to a small perturbation of your problem, random perturbation. Okay, and now the whole thing is to argue about asymptotics of these random perturbations and then apply delta method basically to the Taylor's theorem to sigma, and then you get asymptotic normality, rough speaking. Okay, so in particular, in this example, the image of the solution map is the active manifold, in fact. So all the points that can be written as solutions to small perturbation of the problem are actually on the manifold. So the sample average approximation is very special in the sense that the points it generates actually lie on the smooth manifold. So it's manifold is smoothness. So in some sense, the non-smoothness of the whole problem goes away. This is totally false for projected stochastic gradient method. As you can see in the picture, the points themselves never lie on this manifold on which the constraints are smooth. The constraints are smooth. And this is what's causing the whole difficulty. Okay, so you cannot write down the iterates generated by stochastic gradient method, projected stochastic gradient method, as solution maps to small perturbations of your problem at all. And so in particular, you cannot write them down as they're not lying on this smooth manifold along which the set is smooth and the function are smooth. And so we need to overcome this. This is somehow a fundamental bottleneck. Okay, so to overcome this, I will assume the following. Okay, I will assume the following two conditions. So first of all, I'll assume, just like in nonlinear programming, I still need to formalize this. I need to assume that the image under the solution map of a little small ball is a smooth manifold. So this is just like in this picture. So that smooth little manifold, that image under the solution map of a ball, that's just a little piece of this manifold. And so I'm going to assume that indeed we have this structure in general. So if we forget, this is just an example of nonlinear program, but in general, I'm going to assume that for the problem in question, I have the fact that if I take a little ball, I take a sufficiently small perturbation of my problem, and I look at all sufficiently small perturbations, all solutions trace out a smooth manifold. So these structures are called active manifolds or partly smooth manifolds. There are different names, and they've been around for a very long time. This is just a different way to define them. So there are notions of I've cited a few different papers that are all sort of related, and they're all getting at this similar idea, which is exactly this. So the fact that small perturbations trace out a smooth manifold, and it's really ubiquitous. So there are many examples beyond nonlinear programming, of course, like problems and like eigenvalue problems and so on and so forth. Okay, and then the second thing is new. Okay, this seems to be new in variational analysis. So what's the difficulty? So like I said, let's look at this picture. The difficulty is that we need to somehow utilize the smoothness of we have the smooth substructure that the solutions trace out the smooth manifold, but the points that are generated by the algorithm are not on the smooth manifold, and they bounce across. They behave in a highly non-smooth oscillate, kind of in a very non-smooth way. Okay, so we need to somehow connect. So the idea, of course, is that we need to utilize the smooth substructure in order to eliminate the non-smoothness. But in order to do this, we need to think about, we need to associate somehow to the iterates a shadow sequence, a sequence of points on the manifold that evolves smoothly. So we need to compare basically what happens to the iterates as they cross over this manifold. And if you think about it, the way that the iterates are generated, they're generated by projection. So they have to do with normal directions. So really, at heart, what is happening is we need to understand what happens to the normal cone of my constraint set as you propagate across this manifold. So you have the smooth substructure, you have the smooth substructure. And what's really important is how do the normal directions change as you cross the manifold? And so we're going to put an assumption, and it turns out this assumption is true in a wide in great generality. In fact, it's true in every example that I know, every natural example that I know of where there is an active manifold, it automatically satisfies this condition. Okay, in all natural settings. So it turns out to be a very natural, very simple condition. So I'll just explain it on a picture. So what it says, so there's a formal definition, but let's just look at the pictures. This is our pillow. We have this manifold M. So we're going to say that strong A regularity holds. This is I'll explain this notation in a second. Strong A regularity. What does it mean? It means that if I take any point Y on the manifold near my solution, and I look at the normal cone to the manifold, what's a normal space, at Y. So it's a big set. It's a subspace. Okay, so it's spanned by these two purple vectors. Okay, that's the normal space of the manifold. Now I'm going to take a point X that's not in the manifold, and I look at the normal directions to my constraint set X. That's the green. Okay, so the purple is going to be bigger than the green eventually because of continuity and because of just inclusions. The manifold M is sitting in X, so it's smaller, so its normal cone is bigger. So the assumption is that I'm going to make is that I have a quantitative way to say this. I'm going to assume that the deviation of the normal cone to X, this green vector, the deviation from the green vector to some purple vector is at most on the order X minus Y. It's almost like a one-sided Lipschitz property where one of the base points is moving along Y and the other point is moving along X. So I'm allowing one of the points in Lipschitz continuity of the normal cone to move only along Y, and we're looking at normal to M here, and the other point is moving along points in the pillow outside the manifold. And what I want is that the distance from the green normal cone, the gap from the green normal cone to the purple normal space, is at most linear in the distance between X and Y. That's the assumption. And so this condition we developed like in great detail in an earlier paper, and it's true automatically for nonlinear programming. It's true for cone reducible sets in the sense of Shapiro. It satisfies an eigenvalue lifting property, so it's true for typical eigenvalue problems, eigenvalue sets, and in fact they're generic in the sense that if it's not true for your problem, if you shake your problem a little bit, it will, for almost every little perturbation, this will hold at every optimal solution. Your data is semi-algebraic, whatever. So this, in fact, it turns out to be a very reasonable assumption. It satisfies all the calculus you would want. And in all the cases where there exists some active manifold that are of interest in practice, this condition holds automatically. Okay, so good. So we have these two assumptions: active manifold, strong irregularity. And so this is now the punchline, is that, in fact, we have an exact analog of the Polyak-Juditsky result, which is that if you set alpha k exactly in the same way as before, which is should be a k to the, it should grow as k to the power minus beta, where beta is between 1/2 and 1. And, we can put all those, various assumptions, the standard assumptions to ensure that the iterates themselves will converge almost surely. So as soon as they converge, which almost surely, the average iterate of the projected stochastic gradient method, in fact, is asymptotically normal, and it has exactly the right covariance, which moreover is the same as the covariance, asymptotic covariance of sample average approximation, which we know is optimal, best possible among any estimation procedure. And so as a result, this is unimprovable asymptotically. Okay. So this is the punchline. So this is sort of I stated all the caveats, and this is the answer to the original question I posed. Okay, so I want to just outline an argument. I sort of verbally outlined what an argument would look like, and the conditions on the previous slide. Those are the conditions you need, or we need to make the argument work. And so what's the argument? The argument is as follows. So we have these iterates xk. Okay, these are the stochastic gradient method. And like I said, this is kind of a cartoon of what happens. They crisscross along the manifold. They crisscross. They approach the manifold very, very fast, and this is provably so. So in fact, the iterates. So you see, this deviation is on the order 1 over root k. At least this is the conclusion of the theorem. But in fact, if you look at the distance of xk to the manifold, that decays faster than 1 over root k. So somehow the normal component of these displacement vectors, the normal components to the tangent space at the optimal solution, they go away. They wash out after you take the limit when multiplied by root k, because they go to 0 so fast. So the xk's approach the manifold very, very fast, start zigzagging across it, and sort of on a macroscopic level, if you look away, they kind of start moving tangent to it up to the, until they get to the solution. Okay, so now the point is that we need to utilize the smoothness of M. So we have this very important set M. The fact that it's active, the fact that we have this active manifold, like the ridge and the pillow, that's exactly what ensures that the normal directions shrink faster than 1 over root k. But now we need to understand what happens to the tangent directions. So, okay, so we take our iterates xk, and we want to pass to smooth dynamics. So what we want to do is we want to project xk to M, and let's call those yk. So yk is just the nearest point from M to xk, okay? And now, this is a smooth manifold. The objective is smooth. Everything is smooth. Well, we're solving equations, but the A was smooth. Everything's occurring on the manifold, these y's. So we sort of can understand pretty well what happens for the yks. So the whole thing is to try to understand what did we lose by looking at this projection. And so it turns out, so you can write down now the evolution for the yks. So yk plus 1 is in fact equal to yk minus alpha t, it's the same step size. Okay, in what directions are the yks moving? So the yks are moving, it turns out, in this very simple way, where you look at A and you project it onto the tangent space. The important thing here is that this is a smooth operation. Okay, so we have smooth dynamics, and in fact, if A is the gradient, this is a Riemannian gradient. You're essentially the dynamics for yk are just Riemannian gradients. It's as if you were doing stochastic Riemannian gradient method on the restriction of the problem to the manifold. But okay, of course there is an error because the y's are coming from projections onto xk, and the whole thing is to show that this error is small. Since I'm saying, so I'm lying a little bit here, but essentially what we show is that this error you get after projection, and if you're looking at this evolution for the yks, is only on the order alpha k squared. Okay, and if you're familiar with stochastic optimization, as soon as you see alpha k squared, you're very happy for errors. This is what you want for errors. Okay. And so the whole, these assumptions, in particular strong irregularity, that's where it's used. It's to control this error when you're crossing the manifold in order to describe the dynamics of the y's as being smooth plus an error term. Okay, and so if you do a bunch more stuff, but this is essentially the idea, you get the asymptotic normality. So this is the main idea of the argument. Okay, so now I want to kind of give a broader perspective, and I'll probably stop here because I'm sort of running out of time. So the key condition, just from the viewpoint of variational analysis, or nonsmooth optimization more generally, is that okay? So really, what made the whole thing possible is this condition. Strong irregularity. It's this compatibility, this one-sided Lipschitz continuity of the normal cone. That was very important somehow. And that has nothing to do with the problem at hand. It's a much more general condition, right? It's just this is a condition that just describes non-smoothness of sets. So this did not come out of the blue. Well, okay, it came out of the blue, but then we realized, in fact, it has much more classical roots. In fact, it's related to what is called the Verdier condition stratification theory. So I want to just sort of explain that because it's kind of nice. So there's a subject called stratification theory, which is concerned with completely different questions than optimization, but they're concerned with non-smooth object. And so the basic excuse me, the basic question that one asks in stratification theory is as follows. So I have some kind of a nice space. So a zero set of a bunch of polynomial equations, for example. So this is a zero set of a certain polynomial. I think it's a cubic in 3 variables. Again, the basic question they ask is the following. Well, you see in the picture, this set can clearly be decomposed into smooth surfaces, like into smooth bits, right? There's smooth bits to it. The question is, what's a good way to do this decomposition? And there's the following question. Okay, if you give me a smooth decomposition, is there some verifiable condition that ensures good properties? So in particular, one condition you would really want is you want a decomposition of the set into smooth bits, so that if you walk along a smooth bit, the geometry of the entire set does not change. So for example, okay, this line looks like a smooth bit, right? So if you look at this line, it's clearly important, right? So let's see what happens. If I walk along this line and I sort of look around, okay, if I'm here, the topology of the set locally looks identical. But the situation changes once we get to the origin. Okay, the topology all of a sudden changes. It's a topologically different object. Okay, and so the question they have that they try to answer in stratification theory is, okay, what conditions can I ensure, variational conditions, normals, and so on and so forth, for the manifolds in question, in order to make sure that this topological type is locally constant along these smooth bits. Okay, so in particular, in order to make the topological type locally constant here, all you have to do is exclude the origin. The origin is its own smooth bit. So you're going to have a smooth bit, which is this little ray, this little ray, and the origin is going to be its own bit, and then you have all the rest of the components. This is it by itself, this is by itself, this is by itself, and okay. So that's the decomposition. But then the question is, what are the conditions, the verifiable conditions? If I give you a decomposition that I ask you, what is a verifiable condition based on variational properties like normal columns and so on, normal spaces and so on and so forth, that ensures this kind of what's called equisingularity. So there are two conditions that ensure a type of equisingularity. Whitney, which is it's a condition due to Whitney. I'm not going to state what it is, but it ensures exactly this consistency of topological type. There's a stronger condition, and this Whitney condition has been used in optimization. It's the basis for many things we know and love, like the Kurdi-Kulisevich inequality, the convergence of stochastic gradient to critical points for semi-algebraic problems, the fact that semi-algebraic maps are semi-smooth. There are all these by now known results, and for semi-algebraic problems, and that they're hard. What they're using is the fact that semi-algebraic functions, sets, can be decomposed into these smooth bits, and they all satisfy this nice Whitney condition, which furthermore ensures equisingularity in the topological sense. But there is a stronger condition. There is a kind of quantitative condition that is stronger than Whitney, which ensures a stronger equisingularity. That's a condition due to Verdier. So this condition of due to Verdier is an analog of strong irregularity. So strong irregularities, in some sense, is a very close cousin of this condition of Verdier. In fact, one can really think about Whitney condition as being a cousin of semi-smoothness in optimization, and Verdier of strong irregularity, the way I described it. Okay, and so what I described, and so what I've described is one consequence of this condition in non-smooth optimization, and that's for asymptotic normality of stochastic approximation. But you can imagine there are others, and in fact there are. So we have some other consequences, like we have another paper that tells us, that uses these kind of Verdier properties to argue that we, generally speaking, in non-smooth optimization, algorithms do not converge to only converge to local minimums. They do not converge to extraneous critical points. So we have resolved essentially stating that rigorously, that in non-smooth optimization, if you do gradient method, subgradient methods, it's extremely unlikely that they will converge to an extraneous critical point. It's almost surely under sort of mild assumptions on the problem class, the iterates will converge only to true local minimizers. Okay, and the way we sort of understand that is exactly through these kinds of regularity conditions like over here, because what you need again is to connect non-smooth geometry of like subgradients, all these things, to certain smooth objects. Or it's not what you need; it's what we needed. It's a very nice idea, a nice tool is to be able to connect non-smoothness to non-smooth behavior of algorithms to smooth behavior along certain distinguished manifolds. And there are other consequences that Damek has had separately related to semi-smooth Newton methods and various other things. Okay, so I think I'm gonna stop here and I'll skip sort of the details about that last bit. Thank you.
Okay, thank you very much, Dima. It's very nice talk and very informative about new results, new concepts. You know, again, that's really great, and we have a lot of people who are interested in your talk. Please, any questions to Professor Drusvyatskiy? Any questions? Okay, then if you don't have questions, I have some. Dima, what I'm interested, you mentioned about this tilt perturbations, but I never observed any use of kind of tilt stability or something like that. Anything is related or has nothing to do with these concepts?
Well, I'm assuming tilt stability. So to have these this, right? So I'm assuming that the solution map to the system is going to be smooth. So in particular, it's going to be Lipschitz and single valid. So I'm assuming.
But you mentioned invertibility, which is much stronger, or
yes,
you don't need single valid. What?
Yes, I need not only invertibility. So invertibility is smooth Lipschitz invertibility is tilt stability.
Oh, I see. Okay.
But this is assuming more. It's assuming not only is it invertible in a Lipschitz way, but it's invertible in a smooth way.
Okay, okay. But then could you use criteria for tilt stability in this case?
Yes. So this is just ensuring, you know, that. So okay. So in order to have smooth invertibility, it all comes down to, okay, if you like tilt stability. Plus, you really need an existence of a partly smooth manifold, an active manifold. So if
existence
you combine
of what?
those two things,
say again, existence of what, Dima?
An active manifold. So
active, yeah,
a partly smooth manifold in the sense of Adrian, for example.
Okay.
So one way to define it. So if you put those two things together, this immediately gives you smooth invertibility.
But could you characterize this notion, say, with this addition, say, you know, in some terms which you are familiar with, you know, gross condition or, you know, generalized differentiability condition? Could you characterize this stuff?
Well, in terms of generalized differentiability, yes. In terms of growth, I mean, if you have existence of an active manifold, so the non-trivial thing here is the existence of the active manifold. Once you have that, you have complete characterizations. So it's a really question of how do you characterize the existence of partly smooth manifolds.
Okay, I see. Okay, but say some other results about, you know, you introduce this new type of strong regularity, a strong regularity, which is really, you know, very much impressive. This is wonderful. It's completely new and, you know, very nice. And then you discuss about some relationship with Vinti, with these topological issues. But what about relationship with more standard notions in variational analysis, like say metric regularity, strong metric regularity, or something? What about it?
That's a good question. I don't think it's related. It's different. It's more of So regularity, like metric regularity and all these things, they have to do, with essentially orientation, right? So how where the normals oriented relative to vertical axis and so on and so forth. This is very different. This is more of this is closer to like things like proxy regularity, semi-smoothness, these sorts of notions. These are notions that depend on a geometry, not like they're invariant under rotations and things like this.
Yeah, okay, but Prox regularity, it is kind of second order analysis, and we have characterization. Do you have any second order characterization of this type of condition like you can do for Prox regularity?
No, that's a good question.
Yeah, okay, that's might be useful. For example, for nonlinear programming, I think it's more or less clear, but for non-polyhedral problems, that might be very interesting things to discuss and to develop.
Yes, I agree. Yeah. Yeah. So in fact, while we were doing this, we discovered that this condition of Whitney is exactly semi-smoothness. Okay. But where you so for semi-smoothness, you have a base point. It's fixed, and then you look at x moving around, and then you look at the deviations little low of x minus x star. So with Whitney is exactly this, except x star is allowed to move along a sub manifold.
Okay, that's very interesting indeed. Very interesting observation.
And so Verdier is a kind of is a further strengthening of that. In fact, it implies semi-smoothness. But as far as characterization of this object of this thing being I don't know, but I agree that's a good question.
Yeah, it seems that a lot of possible development is this direction, besides stochastic stuff and projected this gradient methods, really good stuff from variation analysis. Okay, that's wonderful. Please, any more questions to Dima?
Oh, actually, regarding the question for the two function that you were mentioning, you said that so M here must be an active manifold for the two function, right? That means like M is smooth near the point that you are considering, and we have the lower bound in that case or something.
So the active manifold is just this notion. Okay, I defined it in this way, but you could also sort of think about it as it's this kind of non-smooth ridge of your constraints, so that the normal is the optimality, the normal to the objective. Excuse me, the minus the gradient of the objective is supposed to be normal to your set. You want to have this kind of manifold so that basically that outward normal is in the relative interior of the normal space, normal cone at this manifold, and kind of grows exactly like this. So I mean, in fact, this picture for constraint problems is exactly the definition of an active manifold.
Yeah, thank you very much. Yes, maybe some other people.
Dima, can I ask a question?
Yes.
Yeah, that's Alex, please.
Okay. Yeah.
What will happen if the gradient at true optimum point equals 0?
If it's a good question. Let me think.
You will not have an asymptotic normality at all.
We will not have asymptotic normality. You mean?
No, the gradient will be 0.
The expectation of the actual gradient.
Yeah.
It
will be not normal. It's very interesting talk. If you would like, I have some various remarks. We can talk about them.
Sure. Yeah, that would be great. That's something I have not thought about. So, what assumption breaks in that case?
It cannot be. It cannot be.
The active manifold, of course, right? There is no active manifold in that case.
It cannot be normal, and
yes.
This is because you see, for what you mentioned as asymptotic, it's very well understood. It cannot be different from that. Mm-hmm. And in fact, asymptotic normality, when you're on the boundary of the feasible region, happens very exceptional cases.
So under these assumptions, right, in a sense, right?
Exceptional cases, when you see this, you look at the critical cone, and it shows that there be linear space. This is your example, because there are two different convergences here, layers of convergences, and it's very well understood in this stochastic programming. One is convergent. You see this, what happened is that these iterations around that, around the smooth manifold here, in your case, and this is exceptional, were exponentially fast. And it moves slowly at completely different rate along this curve.
Yes.
And it's not surprising. So if the gradient, true gradient is 0, your critical cone will have it will be null. This
Yes.
corresponding, you will not have asymptotic normality. Asymptotic normality in this case, exceptional case, because when you're on the boundary, it's one-sided. What happened in your case? Because you moved a long, smooth curve, and this is very exceptional.
So in what cases? So I guess which examples are you thinking of where the
Think
gradient?
about it generally. Have general convex set, just convex set. Your solution, your optimal solution on the boundary.
Yes.
The fact that the sensitivity of that will be linear if you make small perturbation is exceptional. Usually it will be projection on the critical cone. And the additional term here comes from the curvature of your set. Not surprising at all. It's well known.
Right. Well, the question I have is what example are you thinking of where the gradient really is 0 at the optimal solution?
No, it can happen in your case. The gradient is true gradient 0. Why not? And it's still on the boundary.
Yes, I agree. Okay.
Okay, if you'd like, we may talk about it.
Okay, yeah, that'll be great. I'll get in. I'll send you an email after.
But anyway, it's very nice talk. Thank you very much.
Thanks.
Okay, next probably we are going to finish our seminar. Again, Dima, thank you very much for your wonderful presentation. Okay, and then see you around. Our seminars continue. Just look at the schedule and hope you'll find something interesting for you. We have a lot of people in Dima's talk. I hope it will be continued. Okay, bye-bye.
Bye.
Have a good weekend.
Thank you very much, everyone.